Okay, I think we can get started. Hello, everyone. Welcome to the Hebrew University CS Colloquium. Today, we're pleased to have Sarah Keren with us. Sarah is a postdoc at Harvard and here at the Hebrew University. She received her PhD from the Technion, and she received numerous awards, including the ACAPS Best Dissertation Award mention and the honorable mention for Best Paper. And today we're happy to hear her talk about better environments for better AI. So without further ado, Sarah, the stage is yours.
Thank you. Thank you so much for having me today. I'm very excited to be here and to talk to you about how I think we should work on designing better environments for better AI. So AI is all around us in many applications that have become a part of our lives. It's in security systems trying to detect suspicious behaviors. It's in financial systems trying to help us make better decisions about our money and also detecting frauds. It's in our factories and in our hospitals and in our homes in the form of robots that are trying to assist us perform daily tasks and manufacturing tasks, and it's in the roads. AI is pretty much everywhere. And there is much effort that is invested in perfecting and improving the performance of AI systems. Today, I want us to think of an AI system as being comprised of two main components. We have the AI agents and we have the environment in which they operate. And most AI research focuses on the perfecting and the improvement of the performance of the AI agents, and that is the focus of most of the work in AI, thinking about better algorithms and better ways to make better decisions by the AI agents. But today I want us to think about a complementary paradigm. I want us to think about the environment in which AI agents are operating and thinking about ways in which we can design better environments that take the capabilities and limitations of AI agents and finds the best design that maximizes the performance of the AI agents. So instead of this security system, we're going to think of the airport. And instead of the robot in the factory, we're going to think of the factory and of the hospital and of the roads and of our homes. And we're going to think about design that support the AI agents in the best possible way. So before I move on, let's clarify what it is that I mean by AI agent. An autonomous AI agent is any entity that has agency to perform actions in an environment and can receive from the environment feedback in the form of observations and reward. So such an agent can represent a human if we have a computational model of how a human makes decisions. It can be a robot, which is going to be the focus of my talk today, a robot that has actions and actuators and can perform activities in the environment and collect observations and reward. It can be a software agent. What is common to all these types of agents is that they have to make decisions under uncertainty based both on knowledge they have about the environment, but also based on experience they collect from the environment. And such agents have to come up with a policy, which in its simplest form is a mapping from current states to actions, and have to make good decisions about how to behave. And this is already a very complicated and interesting problem to explore, but my work focuses on multi-agent AI. So settings in which we have multiple agents that are operating in the same environment. And in such systems, we need not only to think about how agents affect the environment, but also how they affect each other and in such cases, we can have various types of interactions between agents. Such agents can cooperate if they have the same goal. They can coordinate their behavior if maybe they have some common objective, but also individual objectives. In some cases, they have different goals, but they want to negotiate with each other to make sure that each of them can achieve the goal. And in some cases, they're adversarials, in which case they compete. And of course, we can talk a lot about each of these settings, but what I want to focus on today is a setting where agents are cooperating or coordinating, and that's going to be mainly what we're going to talk about. And this is also has been a very major theme of my research. What I want to do, my objective is to provide theoretical foundations for designing AI systems that are capable of effective partnership and sustainable and efficient collaborations of both automated agents between themselves and between agents, automated agents and people. And I've done quite a variety of work in this field. I looked at this problem from various perspectives, thinking about how to promote collaborations in various AI systems. And as you can see here, some of this work has been published and some of this work is still in progress. I won't have time to cover all these topics today. I will focus on some of them, but before I move on, I want to kind of clarify what is going to be a common theme of what I'm going to show you today, and what I feel is the DNA of the kind of research that I do and the kind of problems that I like to think about. I like to think about the interaction between theory, between what we can achieve when we provide a theoretical analysis of an AI system, and its relationship to applications. Of course, there are many applications that we can consider, as I said, we're going to focus on robotics today, but I want us to bear in mind the fact that what we're going to care about today is to emphasize the relationship between the theory and the practice, and how practice can also inform the theory that we're developing for a more efficient AI and the efficient design of AI systems. And I'm also fascinated by the relationship between what we know, the knowledge, the symbolic, what we call symbolic AI, and its relationship to our ability to learn from experience. So to collect data from experience from the world and use it to improve our knowledge and vice versa. And this is a theme that is now called neurosymbolic AI. And I usually don't really like buzzwords, but I feel this is actually a really important agenda that AI community is facing, how to combine knowledge and symbolic reasoning with data that we can collect from AI systems. Now, there are many applications that we consider when we think about AI. Today, as a running example, as a common that we're going to use to tell the stories I want to tell you, we're going to use a standard benchmark from the world of robotics called the Robocup Logistics League. And in this case, we have a factory where we have robots that need to take some materials from some location in the factory, process these materials in different machines, and then deliver a product, a finalized product. I'm specifically interested in these kinds of settings about thinking about collaboration. So we're going to have multiple agents, multiple robots, and specifically, I hope you can see me. These are the robots that I've been working with. They're called turtlebots, and we are investigating how our theory, I hope you can see these guys, they're very small, so I could bring them home during this closure. So these robots, we're using them to actually test our theory in practice and see how we can inform our theory for making better decisions for the AI systems that we care about. And these turtlebots are going to appear again in this presentation. And remember, what our agenda here is to think about collaborations, efficient collaborations, and how we can use design to support these collaborations. So, we can think about, in the context of collaboration, we can think about different perspectives, but I really like this citation from Claudia Goldman and Jeff Rosenshine's paper, where they talk about what are the characteristics of collaborating agents, of agents that collaborate efficiently. And what they sketch here are actually three characteristics that we should think about. First, an agent needs to act predictably. Secondly, it needs to share information in an efficient way. And finally, it needs to defer globally constraining choices as much as possible. So we're going to follow these guidelines, and I'm going to tell you about three projects that I've done. One of them is called goal recognition design, where we're using the design of a goal recognition setting to promote behavior that is easy to associate to a particular agent, is easy to recognize its objectives. We're going to use information, and we're going to call it helpful information shaping. How do we share information with partially informed agents in an efficient way such that they can achieve their goals? And we're not going to only think about agents that defer globally constraining choices. We're actually going to think of a more general statement of this objective. We're going to use design and specifically incentives to promote collaboration between reinforcement learning agents. Okay, so before I dive into the details of these specific frameworks, let me sketch the structure of the kinds of problems that we're going to talk about today. So in all of these problems, we have an initial environment with n agents. These can be very different environments, but the common structure means that we have a representation of the state space in which these agents are operating, the actions that each agent can perform, the observation that each agent can make about the environment, that there is a transition function defining, for example, stochastic transition between states, and there is a reward function that defines what each agent is trying to achieve. And in addition, since we're looking at a design problem, we have a description of the set of possible modifications in the environment. So we have some design options that we need to consider, and what we're trying to achieve is to find the best design that maximizes some utility measure. And we're going to look at different utility measures today, but the important thing that I want you to bear in mind is that both the initial environment and the applicable modification induce a space of reachable environments. So what we have in fact here is a combinatorial search in the space of environments. And because we're looking at problems where this space is very large, we need to search efficiently in this space. And I also want you to remember or think about the fact that not only is this space large, but also the evaluation of the utility of each of these environments is going to be very costly. So the simplest problems that we're going to look at today and evaluating the utility for each environment in the simplest setting is going to be p-space complete. So we really need to think about making sure that we search efficiently through this space. Okay, so as I said, today is going to be comprised of these three agendas, and we're going to start from goal recognition design. Goal recognition design thinks about designing environments for efficient goal recognition. So in order to explain what it is that we do here, I want to give you a very simple example, a simplified example of what we mean by goal recognition. And we're going to take this, and for this, we're going to take this very simple airport where we have passengers that are entering the airport from the bottom of the screen. And for the simplicity of this discussion, let's make the assumption that these agents are optimal. So they enter the environment from the bottom of the screen, and we know based on prior knowledge that these agents are either aiming at G0 or at G1. So based on the assumptions that I make about agents' behavior, I know that the agents on the left are going to the left goal and that the agents on the right are going to the right goal. The problem for me is this agent in the center. Not only is she not revealing her goal to us right now, she can actually walk all the way up to the wall without revealing her goal. So it doesn't really matter how much data I throw into this problem and how deep my learning is, I won't be able to understand what the goal of this agent is until she reaches the wall. Now, that is the first step. We have this measure, which we call worst case distinctiveness, which measures the environments in which goal recognition occurs. And now we want to think about the second step, which is the design. So I want you guys to think about how would you, if you had a way to redesign this airport, what kind of change would you introduce to this environment to make sure that it is easy to recognize to the goals of the agents? How would you facilitate the goal recognition process here?
Put a fence in the middle.
Put a fence in the middle. So are you talking about a wall that will go all the way from the entrance to, so kind of like a corridor, you mean?
Something like
Yeah,
that.
something like that. So that's definitely going to solve the problem. It's going, if we have corridors that lead us to our objectives right as we enter the airport, that's definitely a solution and a valid one, but it doesn't minimize another measure that we care about, which is the design cost. So what we want to think about is the minimal change that is needed in this setting in order to minimize the worst case distinctiveness measure. And in this case, based on the assumptions that I'm making about the agents, this won't work every time, but based on the assumptions that agents are optimal, it's enough for me to place this beautiful fountain at the entrance of the airport and recognize the goals of the agents as soon as they enter the airport. And of course, this is only a simple example. What we care about are complex domains, and finding the minimal change is going to be a challenging problem. Now, I told you that today we're not talking about airports, we're talking about these robots. So I want you to now go back to our factory. Now we have two robots that cannot necessarily always communicate. Maybe we just want to minimize communication. Now we want this observer needs to know whether the actor, the other agent in the system, is aiming to the machine on the top or the machine on the bottom. Now, this observer can be another robot, or it can be a person, and we can reduce the need for communication by designing the factory in such a way that makes it possible. Now, with this red block, now the observer will know as soon as possible which machine the actor is aiming for and will aim to the other machine. So I hope I made it possible for you to understand the basic ideas of goal recognition design. We won't be able to dive into the technical details today because there are a lot of other things that I'm excited to tell you about. One more thing that I do want to share is that I told you this very simple story that started with our first work on goal recognition design, but one of the exciting things about this work is that it's gaining a lot of attention, and other people have extended goal recognition, including myself, but also other people have extended goal recognition design in various directions, thinking about goal recognition design in stochastic settings, in adversarial settings, in many different kind of flavors. And also, I'm realizing that goal recognition design is gaining a lot of interest in the goal recognition community, where people are thinking of goal recognition in various aspects and various applications. For example, I have colleagues in JP Morgan that are now integrating goal recognition design into the way they're trying to detect frauds. And we have a book coming out next month about plan and goal recognition, where we cover a lot of the applications. And in many of them, in many of these applications, whenever goal recognition is important, we can think of ways to manipulate the environment in a principled way to promote recognition. So I hope that story was clear. I'm not monitoring the chat, but if you have any questions, I'm very happy to take them. Otherwise, we're going to move to the second story that I want to tell you today, the second dimension of an efficient collaboration, which is something that we call helpful information shaping. And this particular framework, we're gonna use the robots as an example of partially informed agents. So robots are entities that are inherently partially informed. They have actuators by which they operate in the environment. They have sensors by which they perceive the environment, and they have controllers that make decisions about how to behave. But as these robots become more and more robust, we require them to make more increasingly complex decisions about how to behave, and we want them to accomplish increasingly complex tasks. And we have this curse of dimensionality that means that we, as the size of the problem increases, we need to think about various dimensions of the problem, and end-to-end machine learning becomes infeasible. So one approach to tackle this challenge is to think about a hierarchical approach, where at the low level, we have motion planners that decide how specific activities should be performed. For example, in our factory setup, we can use motion planning to understand how the robot should navigate from one machine to another. But at the high level, we have a symbolic task planner that decides what needs to be done in order to accomplish the task. So it needs to understand, for example, that some cylinder needs to be picked up. And the question that we care about in this case is how do we propagate relevant information between these layers, and how do we do this in an efficient way? So today I'm going to tell you two stories about this relationship between task planning and motion planning, two frameworks that I've been working on, and we're going to start with a framework that talks about how motion planning can inform the task planning process. This is where we're going to dive into some technical details, but before that, I want to motivate this framework. So remember, we have our Turtlebot, we have our robot. It's operating in an environment and using its sensors and actuators to navigate in the environment and learn information about it. But this agent is inherently partially informed because it has limited sensings, and its sensors are not necessarily sufficient for it to be able to accomplish its tasks. And in some cases, we may have other agents that are operating in the same environment and have a different perspective. These agents may have other additional information that they can share with the robot that will allow it to accomplish its goal. For example, this can be a drone that's hovering above the location where the agent is operating. It can be a person, it can be just another robot. The challenge that we want to think about now is, in such cases, what is the minimal information that we need to share with this partially informed agent in order to guarantee that the agent can achieve its goal? So we are assuming here that we have a limited communication channel, and we need to selectively reveal information in order to guarantee that the goal can be achieved. We are assuming here that if we transmit redundant information, it's going to just waste resources from this agent who has a limited battery, or maybe that our channel is being monitored by an adversary. We want the minimal information. So the way we are going to model this problem is by thinking first of the environment. In our environment, there is a partially informed agent. And this agent is going to be defined by a logical representation where we have facts or fluent variables, Boolean variables that represent the state of the world. We're going to have actions, which represents what the agent can achieve in the world, can do. And we have a description of information, an initial information that the robot has. And we also have a description of its sensor function. What information can the robot collect from the environment? And of course, we have some goal that the robot can achieve. In addition, we have a description of what are the available information items, facts that can be revealed for the agent. And what we want to know is what is the minimal set of information items that need to be revealed in order to make the goal achievable. And remember, we are looking here at a very large space of options that we need to think about efficiently. Now, this is here a description of basically, we need to think about beliefs here, modeling the representation of the robots, the agents, and the observers' belief, and trying to think about the best way to make sure that what information the agent currently possesses, its current belief, is sufficient together with the sensing that it can perform in the environment, such that the robot or the agent can achieve its objective. I keep saying agent and robot because, of course, this is a general problem that can be applied to various partially informed agents. So this is not a new problem. It's been investigated in the past, and in particular in the multi-agent community, these kinds of problems have been thought of as decision theoretic communications. For example, we can use decentralized, partially observable Markov decision processes to model this problem and think about action, information sharing as actions that agents can perform and reason about in a multi-agent setting. I myself have developed techniques for thinking about this problem in the context of a best first search in the space of design options, and then thinking about pruning techniques that will allow us to search this space efficiently, and admissible heuristics to guide the search. So pruning is removing part of the search space and heuristics in order to guide the search. But today, I want us to take advantage of a specific characteristic of these particular settings. So of course we can model this as a multi-agent setting, like in the decentralized POMDP approaches. But here we can take advantage of the fact that the utility of the observer and the actors are actually aligned, and we can use that to combine these two models into a single planning problem and think about how to, and we can then use a single solution in order to solve our information shaping problem. So what do we have here? On the one hand, we have a partially informed decision maker, and that needs to find the best way to perform some task. And on the other hand, we have an off-the-shelf classical planner, which is guaranteed to find a solution if one exists, and is very powerful and available. So how do we bridge this gap? How do we take a partially informed problem and we transform it into a problem that we know how to solve? Remember, this agent has to think about, reason about in our factory, how to pick up, in order for the agent to be able to pick up cylinder A from machine 8, it has to be at machine 8, and the cylinder needs to be there. But remember that our agent is partially informed. So it doesn't have to be at machine 8. It actually needs to know that it's in machine 8. And it doesn't need to, and the cylinder, it's not enough for the cylinder to be at machine 8. It actually, the robot actually needs to know that the cylinder is there. So we're reasoning here in the belief space. So first approach that we can think of is an approach that performs a transformation of this partially informed problem into a classical formulation that was suggested by Patrick and Bauhaus and Bonnet and Geffner, where we take the original problem and we transform it into the problem in the belief space. So now the set of fluents represent each fluent is replaced by a pair of fluents, by a pair of facts, indicating whether some fluent is known or known to be, so known to be true or known to be false by the agent. Now, we don't only have execution actions, but we also need to account for the reasoning process via the ramification actions, the assumptions that an agent can make about available information using its sensors, so it can reason about things that it can sense, and it needs to know that the goal is achieved. So this is a really beautiful transformation that I really like. It produces, it's a polynomial reduction from one problem to another. It's sound and complete for fully connected domains, and it allows us to think about, to find optimistic plan for these agents, so plans that are based on assumptions for our partially informed agents. However, they don't solve the problem that we care about today, which is the information shaping problem. And there is also no ability to reason about the information cost. Remember, we want the minimal information that is needed in order to solve the problem. And it doesn't reason about the robustness of the plan, which corresponds to our ability to guarantee success of the plan. So what we are going to talk about now is our suggestion to extend this idea in what we call a knowledge acquisition transformation. So we're going to do two things. First, we're going to allow the agents to buy information from the observer. Of course, there is not going to be any interaction. We're just going to use this to model the and allow the agent to only request information that it needs. And this is how we're going to find the relevant information, the information that the agent needs. And we're going to add a cost function to account for the cost of information and robustness. So we take this original problem and now we add to it the helper's knowledge. Remember, the helper's knowledge are a set of facts that are known to the helper, but not necessarily known to the acting agents. The helper is the one that has more information. So we take these and we reduce this problem, we transform this problem into a transform problem called TKA, which has three important additions. First, we only allow the agent to make assumptions that are known to be true. Remember, we want a guarantee here. So we are only going to allow the agent to make assumptions that its sensors are later going to reveal are actually the right assumptions. And remember, assumptions here can only correspond to things that the agent's sensors can assume. If the agent doesn't have a color camera, it cannot assume that it will see that the color of the ball is red. It will only assume things about the sensors that are available to it. We're also going to allow the agents to buy information. So information that is not possible to sense, we allow the agent to buy. And this correspond to the information that we will need to communicate. And in order to account for information cost, we add this cost function, which will associate a cost to add each action in the model. And how do we get our guarantees? We are going to, first, we are going to show, we can show that our transformation, the transformed problem, the TKA problem, has a solution if and only if there is an information shaping intervention that guarantees that the goal can be achieved. And this is actually pretty straightforward once we think about the transformation, because we only allow we introduce into the agent's planning problem information that the actor has, and we make sure that we represent each of these information items in the planning's problems. And as a result of solving this transformation, we also get a solution. So the solution that we get are going to represent information shaping interventions that guarantee that the partially informed actor can achieve its goal. Are we done? No, because we wanted to minimize the information cost. So what we do here is we introduce a cost function. And this cost function can do many things. In particular, it can allow us to think about information cost and trade off information cost and execution cost, but we can also use this cost in many ways. Here we care about information cost and we want to minimize the information shaping cost. So what we do here is we make sure that the cost of a single knowledge acquisition action is more expensive than all other actions that can be performed. And by solving this transformation with an optimal solver, we can guarantee that the agent only buys information that it can acquire otherwise. And this is how we get a guarantee for minimal cost information, the information shaping. And that's fine. But what if there is not enough information? What if our transformation says, well, there is not enough information that the helper can provide the agent with? And this is where we can take the same idea and think about it in various ways. So in our recent KR 2020 paper, we sketched the relationship between the trade-off between the robustness of a plan that is generated by the partially informed agent, and specifically by the assumptions that it can make, and the plan cost. And we show that we allow the user to specify a required level of robustness, and we produce a plan that corresponds to that robustness requirement. We can also use this kind of transformation to inform our adaptive sampling process, or otherwise called the active learning process. We can inform our agent as to where we have missing information. This is relevant to robotics, to reinforcement learning agents. We can use the symbolic reasoning to understand where in the model we collect more information. And David Weiss is a master's student working with Jeff and myself. He's thinking about taking this approach and extending it to probabilistic beliefs. And he's also here in the crowd, and I hope he likes this definition of his overall project. Another project where we're using this kind of analysis is a thesis project by Elad Gershon, who's also here in the crowd, who's from Hebrew U, and with Catherine Whitelin and David Parks from Harvard. Catherine is a senior. They're both thinking about using these kinds of approaches in a multi-robot settings. Remember, the robots that we've shown before are now need to collaborate in an environment and need to reason about what is information that is relevant to other agents in the system. So for example, in this very simple example, we can see two robots. One of them is the red robot that needs to achieve the red goal, and the green robot that needs to achieve the green goal. And there is some missing information. So this this is a map that represents all the available space in the environment, but there is missing information in the center. And this information is very relevant to the green robot, because that, if it knows whether this space is occupied or not, will affect the cost of the plan that it will execute. The red robot doesn't need this information, but can acquire it on its way to its own goal. So what we want to create here is a market where agents can reason about what information they need, and also reason about what information they can sell, in what way they can help other agents, and what will be the cost. So just to kind of clarify how work in this multi-robot system, the dynamics of this kind of work in coronavirus times. This is a project that Elad started around July, where we started working on simulated domains, where I don't know if you can see these, but we have the robots here that are operating. We have the robots here that are operating in the environment, and they have to each achieve some goal, and they have what we see here on the left is we have some partial information, and we want to think about ways for them to achieve or share information with each other in an efficient way. What we're going to see in a second is what we see here is that these robots both have a high uncertainty about the world, but the green, I think the green or the red robot, the green robot now turned around and now has a lot of information about, or has very high certainty about its position, but it doesn't share this information with the red robot, the one that is represented by the red arrows. And we want to think about efficient ways to allow them to communicate. And sorry, okay. So this was in simulation because this was the first lockdown, and thanks to Ziv Bar-Sassad from the Makers Lab, we had a chance to meet at the university and have these robots operate in practice. And what you're going to see here is Elad being very happy about the fact that we managed to get these robots to work in the network of the university. And this joyful dance indicates how hard it was to move. And this was a very exciting moment for us. And now we have another lockdown. So now Elad is working with this robot at home, which is very nice because these robots are very portable. So now Elad is using this robot. It's navigating in Elad's home. And Elad, we couldn't give Elad two robots. So Elad is now the second robot that is trying to provide helpful information. In this case, Elad has placed a landmark in the environment, and it's helping the robot to localize. And what we're developing is a market that will help us reason about the efficiency of this information and the information that the agents can share. Okay, so that was one direction. And let's now think about how task planning can inform the motion planning process. Okay, so now remember, our agents are in this factory. And these green squares that we see are the machines, and we need to generate a plan for the robots to operate. Now, this is a space that we cannot plan in because we need to discretize this space. It's an infinite space, so we need to use discrete positions, which we call configurations, to represent the positions from which each activities can be performed. This is something that we call waypoints. So how do we do this? We take the map of the factory and we use domain knowledge to represent areas from which each each activity can be performed. Okay, so we know that the purple areas are areas from which activities at machine can be performed. And that's fine, that's a standard approach. But what we want to offer here is a propagation of task level consideration into the way we select waypoints. And these performance preferences is something that is not supported in existing literature. What we want to introduce here is a way for us to select, to discretize the space in a way that accounts, for example, for social norms. For example, we don't want robots to block doorways unless it's necessary. Or we don't want robots to block first aid kits. So how do we do this? Well, we create a very dense representation of the environment using what we call a dense probabilistic roadmap. Then we integrate all these preferences into a scoring function. And according to the scoring function, we produce waypoints. And using this technique, we show that compared to other approaches that think about this scoring function, our approach, which creates a single dense representation of the environment and samples from that representation efficiently, we can produce more efficient plans. So what we compare to existing approaches. So we compare to two standard approaches, but one approach failed miserably. So what we see here is our approach, which is called task-aware waypoint sampling, which was an anytime approach. So we could look at the best and first approaches. We compared it against what is called a fixed waypoint generation process. And what we can see is that our framework can adapt, so runs the expected running time is much lower for most of the domains. But not only that, also, we can account for preferences in the most efficient way. And remember, the existing approaches didn't account for performance preferences. They can only account for constraints. We integrated our preferences into the way they select waypoints. And we show that our compliance, which is the green line here, or the green dots, our compliance is the best with regards to these preferences. So I won't have time to show you the videos, but what we see is that our approach does the best job in accounting for these preferences. So the last part of this talk is going to talk about design for collaboration. And these are, something was messed up in the presentation, sorry for that. So the last part of this talk is design for collaboration, where we're thinking about multi-agent reinforcement learning projects or settings. And specifically, we care about sequential social dilemmas where there is a tension between the individual goals of agents and the globally desired objectives. And we're going to see how we're using a version of the robot. So I'm going to use the robots example to kind of demonstrate what I mean. But the actual domain that we're using is called the multi-taxi domain, which you can use. And there we have this, we're thinking about different perspectives, and this is work that I'm doing with two Hebrew youths, two additional Hebrew, very talented master students from Hebrew U. One of them is Ophir. Ophir, which I think is also here in the crowd. Ophir is thinking about multi-agent reinforcement learning settings where we incentivize agents to collaborate. And what we want to show is that such agents are agents that we incentivize to collaborate are more resilient agents. So we are suggesting a new measure for reinforcement learning, which we call resilience, and we are training agents to collaborate. For example, let's go back to our factory example, where we have two tools. And we have two robots, and the green tool has to get to the green machine, and the red tool has to get to the red machine. What do you think, or according to your observation, what is the best way? What is the optimal policy from the global perspective here for achieving this objective? What would be the best way to accomplish this objective for these two robots? Let's say in terms of fuel consumption. How would we minimize fuel consumption and guarantee that these two tools are delivered to their destination? So we have two passengers, right? In this taxi domain, the passengers are the tools, and I want them to be delivered to the respective machines. What would I like as a system operator? What kind of behavior would I like to emerge here?
A takes the green tool to the green station, and B then takes the red tool to the red station.
Right, exactly. But now let's think about a setting where each of these agents has a tray where they can pick up more than one tool. So now we allow the agents to pick up and transform more than one tool at once. What would be the optimal behavior in that case? Now that we have this ability to pick up more than one tool.
Let A do everything.
Everything? I can agree that it picks up both of the tools, but what would be the most efficient thing for them to do in terms of fuel consumption? So A picks up both, and what would we like it to do?
Then goes to red and then goes to green.
But there is B here. How would we exploit B in the best possible way? Wait, you're on mute.
He hands it then. He hands the red tool to B and proceeds.
Exactly. So we would like to see here a collaboration, but in order for this collaboration to happen, there are a lot of things that need to work, right? These agents that now have this a collaborative plan need to coordinate their behavior, right? B needs to wait for A to bring it to 4. They need to share rewards, otherwise B wouldn't wait for A. So they need a mechanism. They need a way for them to agree on sharing the rewards. There are a lot of things that we need to facilitate in order for this collaboration to happen. And what we are doing here is training these agents to collaborate in many ways. And not only are we showing that these will produce more efficient solutions, but what we want to show here is that these kinds of agents that are trained to collaborate are going to have an easier time to adopt to perturbations in the environment. Now, when coronavirus happens to this setting or things fall apart and the model is more constrained, now these agents that learn to collaborate are going to have an easier time to recover. And so the setting that we're looking at here is a Markov game where we have deep reinforcement learning agents that have different rewards, and our interventions are the ways in which these agents can collaborate. So we intervene in different ways, facilitating a collaboration. And what we want to show is resilience. How quickly can agents adapt and converge to an optimal policy? Now, Ophir worked really hard for you guys to see initial results in this work, where we trained ectocritic agents and in a very simple environment, the one that you see here. And we trained them in one setting. We encouraged them to collaborate by allowing them to agree on shared rewards. And in another setting, we didn't allow it. And what we did is we perturbed the environment, and we show that agents that collaborate not only achieve higher rewards, but also they can converge more quickly to optimal behaviors, even when the environments are perturbed. Again, this is very preliminary results, but they show, they give us an indication that this is an interesting path that we should follow. But what if we get unexpected behaviors? What if we train our agents using various deep learning methods, deep reinforcement learning methods in this setting? And remember, the robots here were just an example, but we're using different multi-agent reinforcement learning settings. What happens if the results are not what we expected? Mira, another master's student that is working with Jeff and myself, is thinking about explainability in multi-agent reinforcement learning. So what we want to do here is, instead of intuition-based explanations, which is what I'm calling, what I see a lot in multi-agent reinforcement learning literature, when things don't work, we try to intuitively explain what's going on. Here, we're using formal tools to explain emergent behaviors in multi-agent reinforcement learning settings. So we are using formal environment transforms, such as determinization and state abstractions, that reason about the model, and we apply them to the environment to get the and search for the transformation that yields the expected partial policy. So we can take them to the taxi environment that we've seen before. And if these agents are not collaborating, we can transform the environment and find an explanation that is based on formal tools that manipulate the environment and give us guarantees. For example, we can use transformations that are guaranteed to be refinement or coarser representations of the environment, and these are going to provide explanations for the emergent behaviors. So before I conclude, I want to say thank you, a very deep thank you to my mentors on the that you see here, and I have a group of amazing mentors that I'm very lucky to have, and collaborators with which I've collaborated over the years and have provided a lot of insights, or a lot of course, all of the work that you've seen today has been a result of very fruitful collaborations. And I also want to thank the students that I've been working with. I think this year was a year of lemons, and at least in this respect, I feel like I've managed to make lemonades out of lemons, because I've had the chance to work with very talented students, both from Hebrew U and from Harvard, and it's been an amazing experience. I've also initiated reading groups over these years, over this past year, to make sure that I have a constant interaction with my peers. And also the teaching here has been an amazing experience. I don't think the students realize how important they are for my research, because of the interaction, they move my research forwards in ways they don't even understand. So I'm very fortunate to have this talented group that I've been working with. So to kind of wrap up, my work is about designing AI systems for efficient collaborations. And then, as I've said, we only covered part of the work that I've done over these past years. I'd be happy to think about new ways, and also thinking about works that I haven't covered today. And I hope I conveyed in a meaningful way how important the importance that I view in the relationship between theory and practice in the context of AI system, how important it is to inform the theory by applications, and to take the theory to applications and test it and get some guarantees in the wild, and then go back to the theory and update it according to insights that we get from applications. And the same goes for data versus knowledge, and thinking about ways to integrate symbolic tools with knowledge to make better decisions for AI. And finally, let me tell you what it is that I plan to do in looking forward. So we only touched the tip of the iceberg in terms of what I think we can do in collaborative multi-agent robotics. We only very briefly talked about navigations and how agents can help each other perform navigation more efficiently, but robots have to do a variety of tasks, things about localization, mapping, navigation, and task planning. And in all of these, an efficient collaboration is something that we can think of. And I think markets and game theoretic tools can provide very valuable ways of facilitating these efficient interactions. I want to think of the same kind of ideas in multi-agent reinforcement learning agents, and find ways to promote efficient collaborations. And also, we talk about robots a lot, but I think this is in these kinds of environment design approaches are instrumental in human AI collaborations, and in the different ways robots and AI is going to be integrated into our life. I want us to think about explainable multi-agent AI. There is a lot of work on explainable AI and emerging field, but not enough thought in the context of why specific behaviors emerge. I want us to develop formal tools for explainable multi-agent AI. And I want us to think about using AI in a sustainable way, not just using the resources as if they're infinite. I want us to be aware of the ways we can exploit AI to also minimize our energy consumption, and think about how AI can facilitate a sustainable society. Thank you so much for listening, and I'm very happy to take your questions.
Thank you, Sarah.
Thank you.
Are there any questions from the audience? Okay. Okay, so thank you everyone for attending.
Thank you.
We'll see you in the next talk.
Thank you, guys.
Thank you.
Thank you.
Thank you again. Bye.
Bye-bye.